Alright, welcome to a new day. Let's talk about functions some more, because those are very important to understand how they work and how to write them. So let's talk more about functions in assembly. I just have a bunch of examples for the day, more or less. So let's start out with a question for you. Let's say that this is a function that we have somewhere. Alright, maybe it's we made it in assembly, or we made it in C or C++. Or let's say C. Let's say not C++ because of the name mangling right now. So my question for you is, how would you call this function foo with these two inputs, 42 and 55, in that order? All right, figure out how you would call that in assembly. Go remember, and then also it's going to return an int. Which register can you expect the result to be in? All right. So, yeah, let's talk about it. So, your registers, where you place the first 8 arguments, you're going to place them into x0 through x7, right? So you have just 2 arguments here, so you can place these guys into x0 and x1, but because they're ints, it's w0 and w1, okay? So we're going to move into w0, 42. And we're going to move into W1, 55. Okay, and then we have to BL, right? BL, branch to label, and that's LR and all that fun stuff. BL foo. Okay, that'll make the call. So this is W0, W1 for us. And then the result goes in the X0 register, but if it's an int that you're getting back, it's W0. Just look in the 32-bit part, because that's a 32-bit int that you are getting back. All right, and let's see. You also have to be very careful about this call, because it might clobber things. All right, so foo function calls get to clobber which registers? Let's talk about it. Which folder do I want to be in? Let's do this one. Let's go back to that nice picture that I keep referencing. This beautiful thing. Your functions get to clobber anything that isn't a saved register. So these guys, x0 through x18, you cannot expect to be the same after this function call. All right, x0 through x18. That's a lot. All right. You have no clue what's going on in there. You better not use these again, or you should have saved them on the stack or somewhere special if you needed these again. Don't expect whatever you wanted to be in here still, okay? Especially because, like, the x0 register is being changed by the result anyway, among other things, all right? And then these guys, x0, x19 through x28, they are going to be guaranteed safe. Those are the ones you can use across function calls. So x19 through x28, those are your saved registers. So those ones are safe. Whatever you place there before the function call is still there. Everybody's required to save those values. All right, functions get to clobber these guys. These guys are safe. Okay, so check mark for these. All right. Those ones are safe, and then as functions call on get returned, LR also gets to be clobbered, right, by functions calling other functions, and then like just the BL itself messed with LR, didn't it? And then this special thing called a frame pointer, that is something that I'm not really going to teach in this class. You can read up about it. I would just say stay away from this register, but eventually, if you look at output for that compilers are doing, the assembly output for compilers, they're using this sometimes to like give you an offset into your stack. Okay, so that's that, and I think it's a special little register. All right, but yeah, try not to use it. If you want something still there, use x19 through x28 across your function calls, or save stuff in the stack. All right, so. There's that. Hopefully that makes sense. And yeah, for a lot of these examples that I'm going to give, I highly encourage you to just like pause the video and try it yourself. Okay, that's how you get better. So here are some functions that I'd like to write for you. Again, please try them yourself first if you can. Here's the first one. Let's do a sum array program. All right. Let's do a sum array program, and we will make it work like this. We'll take an array, we'll pass along an array, and the size of that array, and we'll go through it and like add them all up, add every value in the array up. Okay, so for example, if I have this array 1, 2, 3, then if I were to call sum array, on that array and its size 3, it should give me back 1 plus 2 plus 3, so 6. Okay, well, let's make that happen. I would very much like to steal something from before, so let's copy lecture 8. Do we have an assembly file in lecture 8? Show me what's there. Oh, no, 08, sorry. What's there? We have a few. Yeah, so let's copy lecture 8, sum 10 maybe. How about that? To, let's call it sum array.s. And so I'll change it a little bit. And then I'll also have like we'll use like a C++ file to actually call this function, right? Just to make it easy on ourselves. So, oh gosh, what do we want? Let's just clear it all out. Clear it all out. We'll change it. It's not sum 10 anymore, it's sum array. Boop, sum array, sum array. Okay, so there's my function, and this is it, right? This is its, this is how you declare it. It would be declared as, in like C or C++, int sum array, int array, int size. All right, so that's what I have to work with. And let's pretend we have it just for a second and make a CPP file that calls it with the main function. Sum array main.cpp. And so what this will do is it will, well, we need to declare that this function exists, and it needs to be called in the C style, because we don't want to have to deal with those weird, like, those weird label names, right, that are, what's the word? Mangled. There we go. So we have to say extern C in quotes here, and then it'll just use the normal one. This is telling C++ to please use the C style labels. Just BL to sum array, don't like BL to like underscore Z sum array, blah blah blah. Okay, so just use sum array as the name of the label for where this function begins. Alright, so it's declared, and now let's pretend we have it, and we'll use it. So let's make an array. And then we'll see out the result of calling, come on, sum array on A with its size, and its size 7. Alright, so that's what I'd like to do. And so now let's make this function. So what do we got? We got 2 arguments, 2 parameters, and they're going to be in, well, x0 and x1 depending. So this R, we're getting the pointer, right? We're getting a pointer to the start. So this is x0, where that lives. And this one, size, is just an int. So it's not x1, it's w1, all right? That's where that lives. So we have R in x0, and size is in w1 because it's an int. Okay, so I don't actually need to do anything with LR. I don't need to save it on the stack because I'm not calling any functions in this function. I can just use my scratch registers. I'm good to go. Like compute the answer and return it in w0 because it's got to be an int. Okay, so let's put the sum in somewhere I haven't used yet. Let's do w2, I guess, because we're returning an int. We have to work with w registers. W2 0, so this will hold the sum. Alright, and so I'll just loop. I guess I'll use size. The easiest thing to do would just be use size and just like keep subtracting from size until it hits 0, and then I'll know when I'm done. Alright, so let's loop while size is greater than 0. So here's my loop. I first need to compare always. What is my size? W1 with 0. And if it ever is 0, as long as it's greater than 0, I want to continue. And so if it's ever less than or equal to, that's the opposite, right? Then I'm done. BLE, done. And so I'll put done down here. And then now here's like the body of the loop. What do I want to do each time I iterate? I would like to add the current element that I'm looking at into sum, and we'll just use R for that. Like my x0 is always a pointer to a place in this array. So right now, if I were to dereference it, it's going to be a pointer to the first thing, right? Because the address of the array itself is just a pointer to the first element. And then I can just keep adding to this value. Oops. I can keep adding to the value in x0 to get at the next element. I'll just add 4 bytes later, 4 bytes later, 4 bytes later. That'll be nice, right? So add the current element into sum. So I need to load it. Load from x0 into a W register, because it's a 4-byte thing. It's just an int. So it can't be x3, because then it would take 8 bytes and everything would get messed up. I'm loading an int, please, because it's an array of ints. So I have to load into a W register, but addresses always live in X registers because they're 64 bits long. Okay. So there's the current element in W3 now. Let's add it into the sum, which is going in W2. So add into W2 itself and W3. All right. And now I want to get ready to, in the next iteration, get the next element of the array. And so whatever I have right now, I want to pass over it. So I want to change x0 to hold the next place in the array, which is 4 bytes later. So advanced pointer. And then also I want to decrement the size so that I know that I've worked on one. So add x0, x0, it's 4 bytes later. That's the address of the next int, because arrays are contiguous. Okay. And then I worked on something, so how many elements left do I need to work on? It's w1 minus 1. All right, that's one less thing to work on now. And now I'll go always to the top of that loop. Okay, and that's it. Then done is the end. Once I hit there, I've finished with everything, and I've gone through everybody in the array, all the valid things, and so w2 will hold the true sum because I keep adding in the next element. So w2 holds the answer. I want to return that sum, right? Return the sum by saying move into w0, where the answer was in w2, so move w2 into w0, and then ret, all right? And this is going to branch, right? Branch to wherever, whatever the value was in LR, okay? That's the secret. And you don't have to really worry about saving LR, because we didn't call any functions. We can just say ret, so we don't have to deal with the stack even. We can just use our scratch registers. We're happy. All right, so that's the program. Let me show that all to you if I can, more or less. There's the relevant code at least, and then here's the main file. Let's compile together summary main, summary.s into a final file called just summary, let's say. Oh, I messed up. What did I do wrong here? No such instruction. I must have forgot something important. I was unhappy about this line. What did I do wrong? Did a number sign. I did this. Too many references. What in the world? Let's see here. So line 8 is where the first issue is. Move the number 0 into W2 operand after comma got nothing. Weird. Well, I'm not sure what the issue is, and so I'm not going to force you to stare at it with me. I'll take a look, and I'll bring the video back when I figure it out. Okay, I figured it out. It's hilarious, actually. So I'm here to tell you that you can laugh at me. I'm actually not on the class server right now. I am on my local machine, which, I mean, was happy enough until now, because it is an Intel processor. It has no clue about the assembly that I'm trying to write right now. So that's very funny, honestly. Let me take this code and get it on the class server. Boop. That's so funny. All right, there. Now let's go to the class server, where we can actually do ARM assembly. 45. Get that stuff. Cool. CD lecture 10. It's like nothing ever happened. So we've got, let's get both files. Boop, boop. I'll try to get it how it was before. There. Alright, let's try again. So we've got G++, sum array, and call it sum array. Give all those things. What do you know? It works when you're on an ARM machine and you use ARM assembly. So cool. The answer is apparently 38, and I'm willing to take its word for that. Okay? So yeah, that's sum array, and I hope that makes sense to you. All right? So that's how it worked. Here's all the code again, and it actually did the right thing. Cool. So I am currently recording now, right? Yeah. All right, let's try the next one. Let's make a guess the number game. This is always fun. So let's do it like this. So just like this one, this was in X0, this was W1. Let's do guess the number game, and we'll make a program that, like, we can say up to 100, and then it'll play us a little guess the number game, and it will guess a number between 1 and 100, because that's like the number that we pass. And like we'll just ask the user, hey, enter in your guess, and we'll see if it was right or wrong, and like try to give them hints. All right, it'll be fun. So this will rely on a little helper function. Let's make another function called get a random number from 1 to. All right, and this is going to require modulus. So just for our own sanity's sake, we'll implement this one in C this time. All right, and also main. And then we'll use scanf to get stuff because we're using C rather than C++. And then we'll call our function to actually like go get the random number. So we'll call this from assembly. And yeah, I think that's going to be the game plan. So see if you can try it yourself as I explain it more if that wasn't enough. But that's hopefully a good start. So let me steal most of this. We'll make a file called, I guess I'll call this like guess.s. So guess, we'll call this one guess. All right, and I'll get rid of everything. What is its signature? It's going to be, oh, sorry, that's not the name. That's the name of the file, not the name of the function. So this is called guess the number game. That's the function that I'm writing right now. All right, so, boop, oops. How do I want it? Copy, paste, there. Guess the number game, guess the number game. And so this is the function that I'm writing. It's just void, so I don't have to return anything in X0. So we're good to go there. But up to, that up to variable, that my parameter is it's an int, so W0. All right. And then again, let's make a CPP file, or no, it's a C file this time. Let's make a C file called guessMain.c. Standard IO. And what do I want? Well, first of all, I have to declare. Well, I'm making both of these first of all. So I have to declare the one I'm writing in assembly. That's there. And then I have to implement this one, because I want this one, right? And let's see. I want random numbers, so I need to include C standard library, so stdlib.h, and then also to seed a random number generator, I need ctime or time.h in C. Okay? So get a random number from 1 to, what is that? It's just return, you call rand, right? Get a random number from, and you do mod n. This will be a number from 0 to n minus 1, and if we want a number from 1 to n, we just add 1 to that, all right? Remembering to seed our random number generator with srand times 0. So there's that one. And yeah, there's that. And we'll get like up to from the user. Boop. And we'll say printf, give them a little prompt, enter up to. What do you want to play the game up to? And then we'll scanf it. Scanf. An int, please. Store it into up to. So you got to pass along its address. And so now I have that up to variable, and we can play our game. Guess the number game from 1 to that value, 1 to 100, let's say. Okay. So that's it, and this is what the game, like here, let's implement it in C first, honestly. Here's what the game should look like. Here's the implementation of this function. Here's what I need to do. First, I need to pick a random number. Oops. Pick random number from 1 to up to. So that's important, right? Int n equals call our function up to, So now I have my random number, my secret number, and then I'll keep on asking the user for their guess, right? Let's start out the guess with some value that's not ever correct. And then while the guess is incorrect, not equal to the secret n value, I want to keep on asking the user, print f, if I could spell, enter your guess, colon space, and then get it from the user. We'll scanf it into the guess variable. So I got their guess, and now I need to check it. So if maybe their guess is smaller than the number, it was too low. Too low. Or maybe it was too big. It was bigger than the number, the secret number. So we'll print too high. And then otherwise, if it wasn't too big or too small, it was just right. So in this case, we'll say that they got it. Good job. And then also, because they just got it, guess is equal to n, and that will stop the loop too. So that's beautiful. That's the function. So this is what we need to implement now in the assembly file. Okay. So let's do that now. You try it though. See if you can. See if you can translate it properly. I guess if we're going to use this, we need to comment this version out. Comment. Alright, so that's what we're implementing. Well, let's make it happen. So I need to make function calls. Right? I need to make function calls, and I need to keep track of some variables in between function calls, guess and n, in between function calls. So two variables need to get saved on the stack in addition to LR. In addition to LR, because I'm making function calls. All right. So let's do that. So sub sp 16 gives me two things that I could save. And so it always needs to be a multiple of 16, so I need to save 32 bits of things. Or, sorry, 32 bytes. I need to do that. And so I've made room for 32 bytes on the stack. It's got to be a multiple of 16. So I really just needed it as 24. But this is good enough. Right? So let's save our LR, because I'm going to call functions. And that will clobber our old LR. So now I know where to return to. That's good. And now let's also let's save some of our saved registers, because we're allowed to use these. They'll be the same across function calls, but the same applies to whoever called us. Maybe they were using x19 through x28. If so, if we clobber those, we need to restore them. So we need to save their old values. So x19, store that somewhere on the stack, sp plus 8, let's say, and then 20 can be sp plus 16. All right. So that's that, and then I also need to restore these at the end. Let's just do that too. So at the very end, I need to restore these, so let's load them from the stack. So load, and then clean up the stack by adding to sp. All right, add to sp, and then I'll be returning to whatever's in LR now. So that's what happens. That's the end game there. All right, once I'm done with everything. The rest, the body of the function goes in between now. Okay. And I get to use, I needed two things, right? A place to store guess and a place to store n. And that can be x19 and x20. Okay? So we're taking this guy, and we're implementing it here. Well, let's do it. Let's make it happen. All right? So we've got up to in W0 right now. All right? Up to is in W0. I need to get a random number from 1 to up to, so I need to make this function call bl get random number from 1 to, and pass along up to in W0. And hey, it's already there. Cool. So up to is already in W0. Is already in W0, so I can just bl get random number from 1 to 2, and that will be called with the correct up to value, and I will now have in W0 now my secret value n. All right. So we need to save that in a special place in one of our saved registers so that it can stay the same across function calls. So let's move into x19, my first saved register, the value in W0 that I just got back. So save, that's my n value. All right, save n in a saved register. Now I can't go anywhere, so we're good. Then we'll use guess, right? guess in W20, because that needs to be saved as well. So we'll use W20 for guess. It needs to be an int. So move W20 -1. And then here's my loop, right? While guess is not equal to n, do all this. So let's loop. And again, try it yourself first. So I need a loop, and the loop eventually needs to finish. So this is like my done down here as well. But what happens in the loop? I need to do a comparison and then have the body. All right, so let's do my comparison first. So compare W20, because that's guess, with n, which is in W19, right? And as long as they're not equal, I want to do the loop. So break if they're equal, branch away if they're equal. Okay, BQ done. See that? That's the opposite. And now the rest is the loop body. All right. So loop body. What do I need to do? I need to ask the user to enter their guess and scanf it. So I need these strings. This string, and then all these down here too. Too low, too high. You got it. All these strings I need to save in a data section. So let's put them there. So in my data section, I need like an enter guess string as a C string. Ask is enter your guess. I need that one. I need %d, right? Scan format string %d. I need the too low string. Too low new line. I need a too high string. And then I need a you got it string. You got it. All right, that'll work. Dun dun dun. So there's all my strings. I have them now. Yeah, the first thing is enter your guess. Enter your guess, please. Dun dun dun. So, how do I want to do this? Well, we have to be able to printf eventually. And I'm putting the address of the string I want to print out in x0, and that's enter guess. Address at that label, okay? So there's my prompt. BL printf, we're good. And now we need to do the scanf. Scanf %d. So it's going to be BL scanf. And we pass along in x0 the scanf format. That should be 2f, shouldn't it? Scanf format. There. And then in x1 is going to be an address. The address of the place in memory. It's got to be a place in memory, not a register, of where to shove that integer that it's getting from the user. So I need to place in memory. Load into x1 somewhere in memory. Or honestly, I just need to put something in x1 that is my memory address. So okay, what are my options? I have a free slot in the stack right now, don't I? I have SP plus 24 that I'm not using right now. That's a free slot. I could do that. I could use that. That's totally fine. Maybe to make it easier on us, I can just keep using the data section. Maybe that's easier to think about. So let's put the guess somewhere. We'll call it the guess, and that's like a place that's an int. So let's store. It's got to be a word, right? An int. Let's put a dummy value 0 here. So this is space for scanf to set. All right, that'll be the address, the place in memory that scanf will set. So I can load that. The guess, and now this memory will get set with whatever the user typed. All right, each time. I hope that makes sense. I could have used the stack as well. It just needed to be a place in memory. It needed to be an address, because that's what scanf takes. It takes a pointer to where you want to fill in. All right, so that scanf has been called now, and now we need to do our comparison, right? So we need to do our if-else, which means I need to get this guess out of memory first. So I just called scanf. I need to get that guess out. So move the guess into where I'm placing my guess value always. It's going in W20, right? That's where I'm placing my guess value always. Into X20, or W20 for us. Into W20. And so I can do this in any way I want. Let's do like, I don't know, load into, I don't know, X0 again, the guess, and then we'll, it's going to be another load, isn't it? Load into W20, the value that you see at that address in X0, okay? Dereference the pointer. So yeah, this is, right, the guess itself is a 64-bit value. 64-bit pointer. Every pointer on our 64-bit machine needs to go in an X register, but we're reading into a 32-bit register because it's a 32-bit value that we're saving, right? It's just an int. That's why you load into a W register. But your pointers are always going to be in X registers, all right? And now we finally have guess in the right spot. We can do our if-then-elses, all right? So now it's time for the if-else. This is our if-else, else-if-else. Time for that, all right? So let's check, all right? How do guess and end compare? We'll be like, okay, compare W20, that's guess, and W19, that's n, all right? Compare them, and let's see. Just like we did above for the actual loop body. We have to compare them, and then we have to say, okay, we want a less than to be checked this time, right? So less than, if guess is less than n, I want to print too low, and let's see. If it's not less than, I want to try my else if. So what's the opposite of less than? It's greater than or equal to, all right? So branch if greater than or equal to the else if, all right? So if I fall through, that means it was the body of this one. So that's print too low, okay? So let's print too low. This is else if. All right, that'll work. Honestly, it could be easier because I've done the comparison. How about I show you this? This might be easier. You can do this in a bunch of different ways. So let me show you some cool stuff. Let's actually do LT. BLT too low. Or print too low. I don't know how we want to say this. Because I think did I already put too low down here? Yeah, so that's already a name that I've taken up. So it'd be like print too low. And then I can do this, right? I've already done the comparison. The flags are still set, right? If it wasn't less than, maybe I can branch if it was greater than. BGT, print too high, all right? And if none of those were true, I'll fall through, and this is my else, right? This is now print you got it, all right? And then be done with everything. So like, go to the end if. But yeah, we've got like too low, too high, and print you got it, maybe. We can make that its own little label even though we don't use it. Print, you got it. So those are like the three branches. Print, you got it. Print too low or print too high. All right. Print too low, and then print too high. All right. So if we fell through, that was you got it. Otherwise, it's either too low or too high. And we went to one of these. All right. So how do we print too low? How do we do that? It's going to be a printf, isn't it? So printf, we'll do, it's got to be BL printf again. What's the format string? What's the actual string that we're printing? It's just the too low string, so that's going in x0. Boop. So that's that. And then, same for like you got it and for too high. So like all these are here. Print, you got it. Print, too high. But I don't want to do all three, right? I want it to not fall through. It's only one of these bodies that's ever getting run, isn't it? So, like, if it was too low, I don't want to fall through and print too high. And if it was you got it, I don't want to print too low and too high right after that. So it's always go back and be done with the whole thing, like end. So the end of everything. This is the end of the if, right? Let's put that there, and like we're always going there. So BAL end if. Kind of see how that's working? BL end if. This one will just fall through and we're good. But yeah, that's one way to implement this. There are plenty of others, and I want you to try it. All right, try your options. All right. So there's the if else, it's all there. And yeah, once we hit the end of the if, then we're ready, right? That was the end of this whole thing, and that was the end of the body of this while loop, which means we can jump back now, ready to rerun the body. So go back to the start of the loop by doing BAL loop. See if I can zoom out a little bit more so you can see most of this. Whee! All right, so now, yeah, I don't think there's room. It's going to be BAL loop, all right? And so that loop is going to keep continuing for a while. Oop, let's see if I can show you both halves of it, maybe. There it is. There's the bottom. And then here's the upper bit. all right, of the loop itself. So I hope you can kind of see how it's working. But yeah, we mostly translated it, and then we go back to the start of the loop and keep on going until we're done. Right? Once we are done, it's a void, right? We just have a void function that we're working on right now. So we can just immediately return to LR after we clean up the stack and place the actual return address back where it needs to be. All right. So that, I think, should do it. We'll see, though. That's everything. Let's go back to this main file. I can't compile unless I save this. And then we'll use GCC this time. GCC to run this program, to compile. So all those implementation files, we'll call the final thing guess. Oops, I did something wrong. Oh yeah, I used X19 blindly when it should have been W19. Sorry about that. 14. Whee. It's just W19. There we go. And now let's enjoy the fruits of our labor. Enter up to 100, 50, too high, 25, too low, 35, too high, 30, too low, 32, 33, 34. Yay, we got it. So yeah, there's my guess the number game, written entirely in assembly. Glorious. So that's a great example of a lot of stuff. So definitely check this. Get so good at it that you could write it yourself, but that's a good example, I think. All right. So yeah, that's what I wanted to say there. Let's see here. Let's actually go back to SumArray for a second, because there's something I forgot to draw for you. I think that might help. So let's go take a look at SumArray.s, because what's going on is I'm advancing pointers and decrementing size, and there's a reason for that. This was in X0 and W1. So let me show you kind of what's going on. So X0, at the very start of this function, right, we were given the starting address of the array and the size of that array in X0 and W1. X0, W1. So the size of that array was 7, and the array itself was here, right? It was a 7-element thing. And like maybe this is the starting address of the array. The next address is 104, 108, because they're ints, right? They're going in that order. And so X0 held the starting address, which would have been like 100, okay? Whee. And so what we were doing, once we wanted to go to the next thing and look at the next place, always dereferencing X0, I wanted to change X0 by 4, all right? And that's going to let it point to the next, if I change it to 104, then it'll point to the next element, and then I can get that, all right? And then I have 6 things left to look at. So that's why we did, essentially, x0 plus equals 4. That's kind of what we did in assembly, right? And then we decremented the size, right? Then it was w1 minus minus, all right? So that's how that works. I hope that makes more sense if it didn't before. That's why we add 4. That's the next int, okay? And yeah, the reason I draw that now is because we're going to do the same thing by going through the characters in a string, because it's just an array, right? So we're going to convert, so we're going to take a string, the user's going to pass us a C string, so a char star, and we are going to convert that string to all caps, all right, using a library function. There's a toUpper function, okay, in the CC type library, and so we can just call toUpper on like whatever character we're looking at, like that we're placing in W0 or something, okay? So that's how that'll work, and yeah, that's the goal. So I'm going to have a string again this time, and I want to go through all the characters of that string and convert them all to uppercase, all right? So using the BL call. So let's get that started. How do I want to call this? Maybe convert. I think that's what I called it before. So steal this file, convert.s, paste, get rid of all of this, and I'll call it, let's convert to all caps. It's a very long thing. Oop, so it's convert to all caps. Delete that. Boop. Delete that. And then one more. there's my function. All right, so this is this one. We got a C string given to us in x0 because it is an address. All right, so the str itself is in x0, and then I got to do stuff with it. So let's make a main function. Do I want to do C or C++ this time? Let's do C++. Let's I'll steal this one, I guess. Yeah, and that one, and I'll make a new file called convertMain.cpp. Oops, and I guess I can paste this. And then I gotta do extern C, and then give the give this thing convert to all caps. All right, so there's the function. And now let's pretend we have it and try to call it. So let's make a C string. It's a special kind of char array. So hello world. Let's make it all lowercase. Now we want to convert that to all caps, of course. So we're going to call our function convert to all caps, give it the string, the starting address, and then hopefully that str has been changed by the time our function ends, and we can print out its new stuff, right? Give the string again to see out, and it's changed now to hold new things, all right? So that's what my string looks like, and now I've got it in x0. All right, so my goal is, here's most of my string. Let's say, let me just make it short for ease of drawing. Let's say it's just hello rather than hello world. So remember that every C string looks like this. Got your one character, characters. When the string is over, it's the null terminator that tells you when it's done. All right, and then we're passing along the string itself. So we're passing along its starting address. So let's say this is address 100. These are byte addresses. So this is 101, 102, ... All right. So x0 will hold 100 at the start. All right. And we want to play the same game of like advancing it, adding 1 to it each time. All right. But because we're going to call a function, we're going to call a library function, that's going to clobber x0. Well, first of all, we have to give the character we want to capitalize as the first argument to the toUpper function. So we're clobbering x0 ourselves, actually. So we have to save this in a saved register. So we're going to use x19 for that. Okay? That is a safe place to store a pointer to the current character I'm looking at, all right, across function calls. And so that will require us to use that stack, sadly. And so let's steal that from, I guess the number. We don't need all these things. We need like these guys. So let's steal most of these. So convert.s, I need just these ones, paste. And then to clean up, same idea at the end here. Most of these guys, we'll fix it in just a second. And then return. So I actually only need 16 bytes of memory because I have to store LR for sure because I'm making function calls. And then I have to store x19. So just 16. No need for that one. 16, and then return. So that should do it. So now the body of the function goes here. And the very first thing I'm going to do is save my string in a very safe place into x19. So I'm going to move x0 into x19. So now it's safe across function calls. And now what I want to do is essentially, like I want to loop, right? While essentially x19 is like the character that I see by dereferencing x19 and getting a pointer, like getting the byte, getting the character there. While it's not the null terminator, I want to keep on calling toUpper on the character that I see. All right, so that's my loop. So loop, I want to look at the thing that x19 is pointing to right now because that's the string. Right, I want to load a byte. All right. So load a byte into, it's got to be a W register for weird reasons, whatever x19 is pointing to. Take a look at that and compare it to the null terminated character, which has ASCII code 0. For some reason, you can't do this. It doesn't work when you do this. I've tried. The number sign, that thing, does not work for just the null terminated character. It works for every other character, like A. But for some reason, it doesn't work for that one. And so it's just hard-coded its ASCII value, 0. Compared to 0, if it's equal, then we're done. All right, so here's my done down here. And then, all right, what do I want to do? I want to convert that character that's in W1 already to uppercase by calling toUpper on it. It's like toUpper on the character itself, and so the character needs to go in W0. So I'll move W1 into W0, and then I can BL toUpper, and then I will have received back in W0, because that's the return value, the uppercase version of that character, right? Because that's how toUpper works. Whee! If you don't take my word for it, here is C library ctype.each. toUpper takes a single character, returns back a single character as an int. So it really is like correct to use W registers, but we're just looking at the lower 8 bits anyway. So there it is. Call toUpper, we get the character back, the uppercase version, and we want to shove it back into memory. All right, store a byte. All right, so put that character back in *x19. All right, so now it's store a byte rather than load a byte. And it's in, so instead of a load a byte, it's store a byte. And that character is in W0 because that was the return value. Okay, so there it is. And now, just like I was saying here, I want to get ready to work on the next character, right? Advance my x19 pointer to be the next thing. So advance x19 to point to the next character. All right. So that's add x19 1 byte offset. All right. And that's the end of the loop. I always want to go back to the start of the condition because we don't know if we're done yet. So branch to the start of the loop, and there is my loop. Once we're done, we want to restore our stack and our saved registers and LR, and then we can return. All right, so that is going to be convert.s, and let me split screen again so that you can see the main function. Boop. So there we go. G++ compile all those convert files together into a final executable called just convert. And yeah, we get capital hello world. Beautiful. All right. So I hope that makes enough sense. Those are just some fun, good examples of functions. So yeah, let's move on and have some recursive function examples this time. All right, this will be fun. All right, we're not going to do POW because that's going to be in a lab apparently, but I'll do some other standard recursive functions. All right, so hopefully by now you know how to do recursion. I'm not going to review it, but we'll go quickly and talk about how to implement this in assembly land. All right, because you're BLing yourself this time essentially. So the factorial function, you have your base case and your recursive case like this. Your recursive case is, all right, you give me n factorial. The answer is n times n minus 1 factorial. That's how you break it down into a subproblem. And then 0 factorial, we'll just define that to be 1. That's my base case. All right, that's factorial. Let's make it happen. So I'll call this like recursion.s, I guess. So I'll steal I'll keep both these open right now. I'll steal this program and make it recursion.s, paste it in, and I'll actually save the stack preservation stuff because we're going to make function calls. We're going to make calls to ourselves, right? So I need all that there. I need to save LR for sure. So this will be fact, my fact function. Boop. So I got a fact function, and I need a C++ file to actually call the function. So we'll do very similar. I'll steal this file now, and I'll call it recursion dot, did I spell that right? .cpp. All right, paste it in. And then we've got a few things I want to use here. So extern C factorial function, we'll call it fact. So it'll just be int fact int n. That's my function. And let's call it on some stuff. Let's see out like fact5. Make sure it works. So it returns an int. So back to my assembly file. What do I want to do? My fact function looks like this, right? Int fact int n, and it is recursive. So, oops. There we go. what do I want to do? Well, like every recursive function, you got to figure out, am I in the base case or am I in the recursive case? Because if I'm in the base case, I have an answer and I can just be done. So let's see. Let's compare our input value, W0, right? That's our n, with 0. And if so, if it's equal, we're in the base case. If it's not equal, we're in the recursive case. All right, recursive case. And so if we fell through, we're in the base case. And we can move the right answer, which is 1, into our return register. And we'll just go to the end. So we'll BAL, like end fact. All right. So this will be the end of the function, end fact. That just cleans up the stack and then returns whatever was in W0. So that's good for the base case. And now let's have the recursive case. Recursive case. Boop. So what happens in the recursive case? So I need to save something now. So I need to multiply my n by n minus 1 factorial. So I need to make a recursive call and store the answer somewhere. So, all right. This is where x19 comes into play. I'm going to lose, right? I'm about to clobber x0, or sorry, w0. So let's save in a safe place, w19, my n. All right, so this is w19 equals n. It's a safe place. It will not get clobbered because we're saving and restoring it every time. See that? So that's always going to stay n. We're good. And then I need to call fact of n minus 1. So let's compute n minus 1 and put it in w0. It's already, n is already in w0 still. So I'll subtract from w0 the number 1. And so now w0 holds n minus 1. Now I can BL fact, BL myself, right? Recursive call. Because this is going to now, right? This will make the call with my n minus 1 input value, and it will set w0, the return value, to n minus 1 factorial. I'm guaranteed, right, by the magic of recursion, to have received as a return value, which is going in w0, n minus 1 factorial. Like, it's all going to work out. And then how do I use that value? I need to multiply it by my n, which I saved away in w19. Right, so my final return value is, goes in w0, of course, n minus 1 factorial times my n, which I saved in w19. So this is w0 equals n times n minus 1 factorial. That's how we're doing it. Does that make sense? I guess if we want to do this in the proper order, it's got to be w19 and then w0, though it doesn't matter. Now it matches the comment, at least. All right. So that's going to be factorial. All right. So we're just BLing ourselves, right? And we need save registers for sure because we clobber things. We clobbered our input. So let's multiply our recursion files, or not multiply, compile and assemble together into a recursion dot nothing. And yeah, 5 factorial is 120, so it's working right. It's hitting that base case. It's doing the right thing. All right. So let's also do a Fibonacci function. All right. We're going to do the very inefficient one. But the Fibonacci sequence, remember, it goes like this. Let's say it starts at 0. So 0, 1, and then you add them, right? 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 8, ... And let's say that this is Fibonacci number 0, number 1, 2, 3, 4, 5, and 6, ... All right, so we're going to make a function that is called fib of n. All right, called fib of n, and it will give us the nth Fibonacci number. So if I ask for fib of 0, it gives me 0. If I ask for fib of 1, it gives me 1. And those are actually my base cases, because the next one, like this one, you can get by adding these two, but like for this one, there isn't 2 before you. Same for fib of 1. There's 1 before me, but there's not another one, so it can't generalize just yet. So the base cases for Fibonacci are fib of 0, that's defined to be 0, and fib of 1 is defined to be 1. Everybody else, like fib of 2, fib of 6, is the sum of fib of 5 plus fib of 4. That makes 8. See that? That's fib of n minus 1 plus fib of n minus 2. Beautiful. So let's code that now. All right. How do I want to do this? Yeah. So you can put multiple functions in the same assembly file. It's totally fine. But I am going to, there's actually a reason why I said end fact here. Because if I just said end, I'm going to have another similar end in fib. So I'm also going to have like a recursive case. Let's call this, in addition to that, let's be like recursive case fact. All right, just because I'll also want like a recursive case label for the other one. So I think that'll be better. So let's do the same thing. Let's steal all this now. And we'll call it fib. 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 And this is int fib, int n. Okay. So that's how that one works. And so let's declare that it exists over here. And see what we can do. So extern int fib, and let's print out I don't know, fib of what? Fib of 6, let's say. That should be 8. Cool. So we'll call ourselves. So here's fib. A lot of this can stay the same, all right? A lot of this can stay the same. So let's see what we can do. What does fib need to check for? We need to check for 2 base cases this time. So I guess let's just compare with, we got to compare with 0 and got to compare with 1. So let's do them in some order. All right, so it's going to work like this. Let's compare my W0 with, let's say 0. If that's not equal, we're not ready. It's like it could either be 0 or 1. So let's, if it's not equal to 0, let's check the second base case. Check second base case. But if it is 0, we'll fall through here, and the answer, right, if the input's 0, the output is also 0, and that's going, because it's an int that I'm returning, that's going in W0. So it actually already is, right? It already is 0. If so, I'm good to return. BAL, we'll call it end fib. That's my first base case, all right? This is check if n is equal to 0, that's first base case. All right, so that's that one taken care of, and we'll call this end fib this time. All right, end fib. We'll deal with that later. So there's that. That's the start. And then the rest. Let's do the next one. All right, so the check second base case. Check second base case. That needs to happen next, right? We don't know. It may be true or may be false. So now we want to see if n is equal to 1. That's the second base case. All right, n equal to 1, second base case. Compare it to 1. All right, if it's not equal, then it's the recursive case. Recursive case fib. All right, and if it is equal to 1, we will have fallen through, and I want to return the same value as my input again, so I can return whatever's in W0 again. That's perfect. All right, so BAL end fib. And then now we're ready for the recursive case. Recursive case fib. If we get here, we're in the recursive case, we got to make 2 recursive calls, all right? And so actually, I think we need multiple saved registers, because like we have to save our n, right? We need to remember what n was, R6 for example. Let's put that in X19. W0, so save n away. And then I also need to add up an answer, right? I need to save an answer for later. When I make recursive calls. So let's use W20. W20, we'll just start out with 0. That's going to accumulate the sum of the 2 recursive calls. All right, I'm going to need that. So this is where we'll put the sum. We'll put the sum of the recursive calls here. And so that means I need more room on the stack. So I need to subtract 32. It's got to be a multiple of 16. And then I need to save the old X20, because somebody's going to come asking for that later, and they will get mad at me if I mess up. So let's save it there. All right, and then I also need to restore it at the end. So now it's index 20. I save that SP plus 16, and it was 32 bytes that I took off of the stack. Let's add them back. All right, restore. So now we're good. Now we're good. We can make our recursive calls. All right, so now I need n minus 1, fib of n minus 1 plus fib of n minus 2. All right, so my first call to myself, BL fib, BL myself. What goes in W0? It's going to be my n minus 1, right? So W19 minus 1. So that's going in W0. So that'll produce the answer for Fibonacci of n minus 1, right? This is W0 equals n minus 1. And now this is, my answer is going in W0. The return value is the result of fib of n minus 1. Sorry, fib of n minus 1. Perfect. And then I want to save this answer into W20, so I'll add it in. W20 W0, because that was where the answer was. Perfect. Right? So that's the n minus 1 call. Then I want to do the same for n minus 2, fib of n minus 2. Call that and add it in. Right? Because that's the two recursive calls. Let's do n minus 2 now. So sub 2, n minus, oops, oh gosh, n minus 2, fib of n minus 2. Add the answer in. Perfect. And so now, W20 holds the sum of fib of n minus 1 and fib of n minus 2. I called myself with a BL myself. So now W0 holds the answer. All right. W20 holds the answer because I'm adding it into there. And I need to return that because I'm returning an int. So move into W0, my answer, which is in W20. All right. And then I'm good to restore everything and return. So that is going to be my very long Fibonacci function. So scrolling through it slowly, hopefully you can kind of see what's going on. In theory, that should work and give me back 8 if I recompile. Oops. Yeah, I do get my 8. So cool, it's working, it's hitting the base case. This is a very inefficient implementation though, as you learned about in CSCI 41, right? But that's okay, it's just an example of recursion. So, just like Fibonacci can be made faster by just like looping, you can actually get away with using recursion and like getting the beauty of recursion, like the ease of implementation of a lot of recursive algorithms, and then also the speed of a loop just by using a fancy compiler. It's really, really nice. So I want to talk about something called tail call optimization. All right. So this is an advanced topic, but I want to teach you a little bit about it. All right. Recursive functions usually require the stack to execute, right? Like for this one, for example, how do I want to say it? Yeah, let's say that we have this sum function. Let's say like we want to sum up all the values from like 0, like let's say this is my problem. Sum of n, like I want to produce a function called sum of n that adds up all the values from 0 plus 1 plus 2 all the way to n. All right, that's what I like to do. So this is one way to do it. This is like a fancy way. I'll get into that. But like the normal way to do this, if you were going to do it recursively, would be like, all right, my base case would be like, you want to sum up all the values from 0 to 0? That's just 0. Cool. Recursive case would be like, you want to sum up all the values from 0 to some I? Well, first, sum up all the values from 0 to I minus 1. There's your recursive call. And then add in I because that's what you forgot. All right, so that's like, you could translate this very easily to a recursive function, right? And so you could just ask for sum of 5 or something. And that you'd have to make a bunch of stack calls, right? You'd say sum of 5 would call sum of 4, would call sum of 3, and they're all waiting on each other. 3, 2, 1, 0, and then it's kind of like works its way back up. But like you're wasting a lot of space. Like you have order of n calls to your function, right? It's a big space complexity there, and so it takes a while. So it wastes some space. It uses the stack to execute, right? You got to save your LR all the time. This is wasting space, and it also wastes time, all that copying. So wouldn't it be nice if we weren't punished for thinking recursively? That would be so cool, because we like to think recursively. There are some algorithms just like only make sense recursively. So there's a way to rewrite pretty much every recursive function to enable what's called tail call optimization. So first of all, here's a different kind of sum function. It still does the same thing, but you got to call it slightly differently. You're still going to say sum up all the values from 0 to n, but you're also going to have a second argument, and that will start off being 0. That's going to be your accumulator, okay? And 0 because we don't put anything in it to start. So if I is 0, if you got down to your base case, return what you've accumulated. Otherwise, return the result of summing up all the values to I minus 1, and your accumulator should hold whatever it held before plus I. So it's building up a value each time, building up a value each time. So I encourage you to run this and see that it does the same thing. And this is called, like when you return the result of a function call, that's called a tail call, right? Because you don't have to save any variables around for later. It's like whatever the answer is, whatever the answer is, whatever this gives back is the answer for this function too, right? So you don't actually need to make a bunch of stack frames, right? So do you see how there's no work to do after this function call returns? It's just like return the answer. And so we say that the sum call is in the tail position, and the compiler can translate this call to be just like, all right, I'll mess with the values in W0 and W1, and I'll just jump back to the start of the loop, to the start of the sum function. And it makes it a loop for you. Isn't that beautiful? You can translate it as a branch, as a jump, rather than a function call. It gets translated into a for loop for free. So you can, you have to enable higher optimization, -O2 to G++, and it will turn it into something like this. All right. So it's like, all right, it makes up some weird label values, but do you see how there's no BL anywhere? It's like, all right, in the base case, it's going to do some weird comparisons, and like it'll skip over things. But here's like the recursive case. You can see that it's adding to like the like it's going to subtract from the value because it's placing it in a special place, placing in W2 for some reason, subtracting, and then it's adding into the accumulator, which they put in W0 for another weird reason. That's the compiler, don't ask me. And then it branches right back to the start of this label. It made a loop for you. Isn't that cool? It makes it really fast, all right? So let me prove to you that this does the same thing and that you don't actually need any stacks, all right? So let's say that we want to add up all the values. Let's say that we want to call like sum, let's say we want to call sum 3, 0 to add up all the values from 0 to 3. All right, that is going to call, right? What's it going to turn into? It's going to return, in the recursive case, it's going to return the result of calling sum 2, 0 plus 3, so 3. And what's this going to do? Again, recursive case. It's going to return the result of calling sum 1, and then it's going to be 3 plus 2, so 5. Okay? And then it's going to call sum again. Sum all, it's going to return the result of calling sum on 0, right? I minus 1 is 0 plus 5 plus my 1, which is 6. And then it's going to return, all right, if I is 0, it's going to return the accumulator, so it's returning 6 as the answer. And that is the sum of all the numbers from 0 to 3. Okay? And so, naively, a programming language that didn't know any better could do this. Like it'd be like, all right, call sum 3, 0. Okay, cool. Then all right, we got to call sum 1, 5. Got to make new space on the stack for that. That needs to call sum, no, sorry, this is 2. I got my numbers wrong. Sum 2, 3, excuse me. And like, okay, that needs to call sum 1, 5. And then that's waiting on sum 0, 6. And then once that returns, like I can just like keep on giving it back to the person below me. Keep on giving it back, keep on giving it back, then I'm done, right? But actually all of these are redundant because the answer to this is the same as the answer to this. And so smarter compilers that have optimizations turned on, can do the following. They can be like, all right, you called sum 0, 6. I know that you're calling this in tail position, so I'm just going to replace the stack frame. Sum 0, 6 become sum 2, 3. Oh, sum 2, 3, you need to do more work? It's a tail call, so I'll replace the stack frame with sum 1, 5. Okay? Oh, 1, 5, you need to do more work, but you're in a tail call position? I'll just loop, and I'll reuse the stack frame, sum 0, 6, and then you're done, you can return. Right? That's how this works. All right? It's very beautiful. It's wonderful. It's O2, and I can prove that to you. There's actually a wonderful website. If I haven't showed it to you yet, it's called godbolt.org. It lets you see what compilers are going to give you back as assembly. So let me show this to you. It's a wonderful thing. So here is, oh my gosh, of course. Of course, every single space character is messed up because this is how PowerPoint works. It copies and pastes really weird things. So let me use this for a second so I can copy and paste these weird space characters away. So let me substitute anytime we see that with a normal space everywhere. Please and thank you. There. You better be happy now, please. There we go. So here is save that. This is really nice. You can change which compiler. By default, it's not ARM. So I search for ARM 64 GCC, and you just pick the latest one. I picked the trunk. That's like the latest version. And then here it is. It's saying, all right, here's some of these two integers. Here is the default. Oops, get rid of that. Get rid of the compiler options. Here is the default way that it's being compiled. And you can see that it is saving LR and stuff on the stack. It's like your X29 or whatever. And it's doing BL. It's doing it the naive way. But if you enable -02 high level optimizations, it got rid of the calls. It turned it into a loop. Isn't that glorious? So yeah, that's what I wanted to say. I'm not going to test you on this idea, but it's a really cool thing, right? You can write a recursive function. As long as you write it in this kind of way, it gets translated into a loop for you, and you don't have to pay the price of recursion, but you get the benefits. Isn't that nice? So yeah, that is that's the answer. That's the idea. Okay, so I think that's where I wanted to stop for the day. It's time to give you a new lab, but we'll do that in the lab introduction video. So I'll see you then.